Good afternoon, everybody, and thanks for coming. To set the stage a little bit, I want to begin with what you probably already know. Hadoop and its ecosystem tools have become increasingly crucial for businesses of all types. And this is in large part for its promise of providing a way to unlock value and insights from your data at massive scale. And in particular, to do so with unprecedented agility, right? So that you can quickly react day to day to changes in the landscape of your industry. Now, since you're here today in the session, you've probably also encountered and maybe dealt with yourself personally too, this unfortunate fact that your administrative overhead and operational complexity of managing your Hadoop infrastructure is also scaling up. And perhaps superlinearly with the increasing sophistication and diversity of your workloads. And this is something that threatens to undermine the very value proposition that it brings in the first place by eroding that agility. So that's where Google Cloud Platform and Cloud Dataproc come in. We'll see how a migration to cloud and an incremental reorganization of the way you think about your Hadoop infrastructure and your Spark workloads can let you preserve all the power of this open source stack that you've built your systems on already, but also to remove those brick walls and let you get back to focusing on your data, focusing on your insights. So my name is Dennis Huo. I'm tech lead of Google Cloud Dataproc. And in today's session, we'll be going over deep dive, end-to-end, of what it looks like to migrate your Hadoop and Spark workloads to Google Cloud Platform. Now, along the way, we're going to find that no steps really have a one-size-fits-all answer for everything. But rather, we'll be focusing on some overarching guiding principles and reusable building blocks that you can use to build the right migration strategy for your business needs. So let's begin with what is Google Cloud Dataproc. Dataproc is Google Cloud Platform's managed Hadoop and Spark service. Its overarching goal is ultimately just to help tip the scales away from having to think about Hadoop as low-level infrastructure. So to help illustrate a little bit of what it means to be fast and easy and cost-effective, imagine, if you will, the next version of Hadoop or Spark comes out, right? It's a shiny new version, promises something like a 10x speedup of all your workloads, or say, can simplify one of your 10-stage pipelines into a one-liner in Spark. So just consider, what might it take to go from that time where you've heard about these versions and want to try it out, to being able to deploy this, to canary this, and be ready to switch over your production pipelines to the latest and greatest at full production scale? Well, with Dataproc, it should be no more than a one-liner on the command line, or alternatively, just about 4 clicks on the cloud console. And about 90 seconds later, you should be up and running with the latest and greatest, ready to canary your workloads, even at full production scale. And this same kind of speed and simplicity is also what lends itself to cost savings, ultimately, because you can more easily ensure that you're only deploying the resources that you need when you need them. So right off the bat, you can significantly reduce your cost just by making sure that you're actually paying for what you actually use. To put this in perspective in the big picture, ultimately, there's a whole spectrum of approaches to running Hadoop on Google Cloud Platform. And this ranges from thinking about GCP as your infrastructure to thinking about GCP as a platform. Now, along this whole spectrum, Google works with third-party Hadoop vendors and provides open-source connector libraries and tools so that, in general, your migration doesn't have to be an all-or-nothing proposition. Now, some of the concepts that we're talking about today are going to be applicable no matter what kind of approach to Hadoop on GCP you take, while others are going to be highlighting new architectures that are made possible by moving to this fully managed Dataproc side of the spectrum. Taking a peek under the hood at how Dataproc is made, Dataproc layers in features in between the layers of the underlying Hadoop stack, and adds these features for easy visibility into status and monitoring, adds control hooks and configuration hooks for things like managing your clusters, resizing your clusters, optimizations. But it does so on top of the open source interfaces of the Hadoop stack, ultimately. So what this means is Dataproc adheres to the principle of letting you drop down one level into the lower level stack whenever you need. So you don't have to abandon any of your low-level custom advanced customizations if you don't want to, just to get the value-added features of Dataproc. You can bring all that with you and still keep those low-level customizations. So as an example here, we have Dataproc clients and raw Hadoop clients. So if you want, you can interact entirely with your Dataproc clusters using the standard underlying raw Hadoop clients connecting over TCP. And if you don't want to, you never even have to acknowledge the existence of Dataproc's Jobs API. On the other side of the spectrum, you might choose to only interact with your clusters through Dataproc Jobs APIs, through these standardized web-based REST interfaces, and never even have to be the wiser about VMs existing under the hood at all. So, but both of these options are available. Dataproc's Hadoop distribution is based on the open source Apache BigTop project, and natively will install and support Pig, Hive, Hadoop, and Spark. Other ecosystem tools like Tez, Zeppelin, and Kafka can all be activated from the Dataproc distribution using something called initialization actions, which are just scripts that you can use to customize your Dataproc clusters for your own needs. So that brings us to planning a proof of concept, or a POC. Thinking back to that on-premise static cluster, you may find yourself becoming increasingly dependent on increasingly monolithic Hadoop clusters. And in a lot of ways, some of the key strengths of Hadoop as a great data platform are also the source of its weaknesses. And what I mean by that is there are all these components in the Hadoop ecosystem that make it so easy. They're so well integrated with the rest of the Hadoop stack that it's easy to augment your existing Hadoop cluster with powerful tools like Oozie for scheduling, or Zeppelin, Jupyter for data science, maybe various Hive Server 2 clients. And along the way, you don't really notice, but then one day you'll look back and you'll see that somehow you've dumped all this systemic complexity in one place on your cluster and loaded it down in such a way that it's that much more difficult in aggregate to now reshape or re-architect your workloads when it becomes necessary to do so. So what this means for your POC is, as you're thinking about how to migrate, you want to make sure you're not just thinking about forklifting your entire Hadoop stack onto GCP, complexity and messy hacks included, but instead you want to think about keeping your eyes open for opportunities to simplify your architecture as you go. So, this is something that, as you keep in mind that clusters aren't an end unto themselves, that no single cluster should really, you don't want single clusters to constitute your entire data analytics universe in a sealed, hermetic way anymore, right? You want to think about the broader platform on the whole. So for example, you'll use clusters as building blocks towards your greater data platform at large, and perhaps you'll use BigQuery for the bulk of your data warehousing needs. Maybe you'll find that Stackdriver is the easiest way to unify your logging and monitoring across all your GCP services. Now, as one of the first steps towards your POC and subsequent migration, you'll want to make sure that you outline your high-level goals, the driving forces of what you're trying to get out of your migration to GCP. And typically, these are going to be high-level goals that can be achieved in any number of ways. So for example, if you're thinking about cost savings, you want to make sure you're thinking about price performance and total cost of ownership, instead of getting stuck on comparing CPU for CPU or byte for byte storage. Another example, in terms of scaling elasticity, if you're unlocking this elasticity, GCP isn't just a way to speed up the hardware requisitioning cycle, right? It can be a faster way to requisition hardware in a traditional way, but really, you get the most mileage out of larger architectural changes. So for example, by separating out your storage and compute and scaling them independently, or separating out different workloads, scaling them independently. This is how you can achieve the best the best scalability for what you've paid for doing this migration in terms of making changes to your architecture. Now, these are just some examples of goals that you might come in with and how GCP features might relate to them. Ultimately, you know best what your driving goals are, and this is how you will shape your overall migration plan. Now, it's probably also worth mentioning right now, I know I've been talking a lot about change, change this, change the way you're thinking, change your architecture, and admittedly, it's scary to talk about change, right? Like, change comes with cost in itself. It can be a source of complexity in itself. And it's definitely a valid concern to think about the cost of change. But what's important is both, you should neither write off change altogether, nor should you blindly accept change as good. So it can be good, it can be bad, but it doesn't have to be a significant cost. And there are definitely opportunities here, during your Hadoop migration especially, for low-hanging fruit where the cost isn't that significant and you have significant benefits for the long-term viability of your architecture. So as long as you're weighing those costs and benefits, that's what's important, even if it doesn't always land on the side of choosing that big architecture change. As long as you know what's going into that decision to do so. On a more concrete level, you'll want to identify as much of the characteristics that go into the requirements of your long-term architecture as possible. So really characterize your existing stack and figure out what you're doing. And I focus on this, on the characteristics, less so than the requirements, because ultimately you're not just coming up with a checklist of requirements. By characterizing your stack, this is a great opportunity to identify what components you really love and which ones are really providing you value long-term and will end up in your long-term architecture. While you'll find that a lot of things are really just workarounds or a means to an end, right? That actually bring you pain, but were a necessary evil in the meantime, and something that you can really slice out complexity with by doing your cloud migration and adopting something a little more cloud native for those pieces. On a more practical level, the logistics of planning out your timeline and capacity planning, that's something that you'll want to do early on as possible in your workflow. So coming up with your estimates of what you'll need over the course of your migration to make sure that you're not suddenly blocked by something silly like a quota request when it comes time to actually ramp up your migration. So that brings us to data migration. This is one of the first concrete technical items that you'll be tackling during the course of your POC and migration. The cornerstone of all your migration is likely to be the Google Cloud Storage connector for Hadoop. So this is a connector that Google provides and implements the Hadoop file system interfaces on top of Google Cloud Storage. So we strive really for out-of-the-box compatibility. So this means that for the most part, your migration will take place using familiar Hadoop tools that you're already using inside your Hadoop stack, running simple dist CP jobs into GCS. Other options that we provide include HDFS on persistent disk, which comes standard with Dataproc. Or alternatively, you might consider using local SSD as a higher performance alternative. So good for things that require, where you might want to pay a little bit extra in order to guarantee very low round-trip latency for things like business intelligence or online data analytics. Slightly larger architectural change involves potentially replacing your entire HBase cluster with Google Cloud Bigtable. So in the same vein as GCS being a file system replacement, Google provides HBase compatible clients for Cloud Bigtable so that you can transparently migrate over any workloads that normally run against HBase and use Google Cloud Bigtable instead and treat it like an HBase cluster. And this is something that will drastically reduce your operational complexity by no longer having to manage your HBase cluster yourself. Another option is using BigQuery for your data warehousing and SQL-based analytics. So in the same vein, we provide connectors for BigQuery for Hadoop so that you can still interact with your storage in BigQuery while doing the bulk of your data analytics in BigQuery itself with zero ops, without managing your clusters. Timeline-wise, some of the data storage plans that you take on will help shape your migration strategy in itself. So as an example, one recurring pattern is you might find that you're archiving data into GCS, or you might find that regardless of how you want to migrate your workloads, you're starting to do disaster recovery backup into GCS. So in these cases, it's very natural to start adopting ad hoc use cases inside of Dataproc. So now that your data is already there, you might find that an unexpected unexpected backfill comes up, and you can use Dataproc to get that done quickly. Or maybe new pipeline development, where you don't want to occupy space on premise. It's a natural fit for using ad hoc Dataproc usage. Digging a little bit deeper into the compatibility of GCS and HDFS, like I mentioned, the GCS connector is designed to be compatible for the vast majority of Hadoop use cases. So drop-in replacement, anything that uses file input-output formats, Spark, text, binary files, all of these things just work without you having to think about it. That said, there are some caveats, right? Because Google Cloud Storage is an object store, not a file system. And this is something that's becoming also increasingly common within the Hadoop ecosystem itself, is to use these object stores. So different cloud providers and private cloud solutions like OpenStack Swift also have similar object store semantics. And this is something that's recognized and becoming better supported within the Hadoop community itself day to day. So that'll get better, but in the meantime, it means that there are some more specialized HDFS features that might require still using HDFS. This includes directory semantics, right? So an object store doesn't actually have directories, so you don't have things like directory access times. Additionally, objects are immutable once they're created, so one use case that might still do well on HDFS instead of GCS would be if you have a workload that requires appendable files. In general, though, a lot of these constraints come from architectural designs that are actually benefits. So for example, some of this increased round-trip latency comes as a result of no longer having any single point of failure or any single bottleneck. So you can have arbitrarily many files in a single GCS bucket if you want, in a single GCS directory, because it's all massively distributed on Google's infrastructure, right? And as an implementation detail, that means there's an extra layer of indirection, which is why latency might take a little bit longer round trip. In general, the same principles for optimizing your HDFS workloads applies to GCS as well. So just using small files can hurt in terms of round trip latency. So avoiding lots of small reads, avoiding lots of sequential small metadata requests, using bulk reads of data whenever possible, all still equally apply to GCS. So to visualize what it might look like to actually run this data transfer from your on-premise cluster into GCS, there are generally two categories. You can have push-based or pull-based transfer of your data. The most straightforward way here is push-based, where you simply install the GCS connector on-premise and use the same public APIs to access GCS as any other client. So this is a very straightforward approach, as long as you can modify your on-premise cluster and you have some spare capacity for running, say, distcp MapReduce jobs. And this will just push everything over your public internet gateway into Google Cloud Storage. And in transit, everything, GCS requires HTTPS, so everything's protected by that SSL layer. As an alternative, if you can't do that, you can set up a cloud VPN gateway to bridge your on-premise network with a compute engine network. So Dataproc supports deploying your clusters into custom subnetworks that have all the IP address and firewall rules that you need to make your VPN work. So once you've bridged your networks, Dataproc clusters being built on raw native compatible Hadoop clients can, out of the box, interact with your on-premise cluster and pull data out through that VPN tunnel. So you simply specify your HDFS // on-premise name node path, and everything just works. And one benefit of running Dataproc clusters like this to pull the data out of on-premise is that you can use Dataproc's cluster sizing features in order to adjust your transfer rate as needed too. And this also doesn't have to be putting data into GCS. You might be performing these transfers into HDFS on Dataproc instead. So that brings us to some overarching cloud architecture concepts. Like I mentioned before, there's no one-size-fits-all answer. So again, these are just some building blocks that you can assemble into your own migration strategy. But these are recurring patterns that are well utilized in a variety of places. So to begin with, I want to think back again to that on-premise cluster. And traditionally, Hadoop places a lot of emphasis on data locality and bin packing and things like this, right? And it makes a lot of sense in that it's common to come in and provision a cluster and plan out a Hadoop cluster based on storage size. So you'll say, I need like an X petabyte cluster, and that's a certain number of disks, and you can adjust your CPU and RAM a little bit. But in large part, you're still driven by saying, like, you need X petabytes of storage, right? And you just have to plan to then make do with what compute comes with it, for the most part. And ultimately, this is a leaky abstraction. This is letting storage implementation details start to dictate application layer decisions of how your workloads are shaped and how your workloads are sized. So on Google Cloud Platform, you don't have to worry about bin packing, right? That's Google's problem to worry about. And instead, you can separate out your storage and compute. And not only do you get your cost savings by only having to pay for what you're actually using and having independent scaling, this actually also simplifies your workflows, because you don't have to worry about shaping your workloads to the right size for your hardware anymore, but rather you do it the other way around. Pick the right hardware for your workflows. So this is a concept that actually unlocks a lot of other architectural concepts as well. And to put it in terms of number, imagine if you have a job that takes, say, 10,000 vCPU hours. On cloud, it costs the same whether you provision 20,000 vCPUs for half an hour, or if you provision 100 CPUs for 100 hours. Right? The math works out. Yes. So in that case, it costs the same, but that data is so much more valuable to you now rather than later. So you don't have to try to slip it into some spare capacity and let it run inside between the cracks of some existing infrastructure. You just burst into the cloud and get the job done immediately, so that you can have the data as quickly and as valuably as possible. One nice feature of Compute Engine that Dataproc natively supports is preemptible VMs. So preemptible VMs are just like any other VM. They operate just like any other VM. The only difference is that Google reserves the right to reclaim these VMs and to reclaim them, preempt them, if other on-demand or production workloads make it necessary, right? And as a result, they only cost 20% of the normal cost of a VM, so significant cost savings. And normally, it might be difficult to manage these kinds of things, joining and leaving your cluster by yourself. But on Dataproc, that's Dataproc's job to make sure that it requests that it replenishes these VMs if they leave the cluster, and to make sure that they smoothly join and leave the cluster over the course of your workload. So that means that it's basically just fire and forget. You set your number of preemptible VMs on your Dataproc cluster, let the job run, and you get better price performance. Another compute engine feature that Dataproc natively supports is custom VM types, which which Urs talked about in today's keynote as well. These again go back to the notion that you don't have to worry about bin packing. That's Google's problem. So you don't have to worry about stranding resources because of an oddly sized workload, or having to under-provision for a given workload, right? Pick exactly the right mix of CPU and RAM that you need, and Dataproc will work it out. Dataproc will dynamically calculate the right Hadoop and HDFS configs based on the actual requested amount of CPU and RAM. One of the bigger architectural concepts that is enabled by that disaggregation of storage and compute. And I mentioned this a little bit before too, is that you don't want to think about single clusters as your entire universe, right? Like, you don't want your Hadoop cluster to be your hermetically sealed data analytics universe. Instead, the broader platform as a whole is your data analytics platform. And so in this concept, you'll separate out different workloads into different clusters. That way, this eliminates a lot of this multiplicative complexity by where you try to bin pack a lot of different things into the same place. So you can significantly simplify things that way. And what's more, you can independently optimize these. So for example, you might find that some workloads, like say your business intelligence or your online analytics, prefers paying a little bit more for very high performance and very predictable performance. So you might opt for something like HDFS on SSD and cache a lot of your data sets inside of that HDFS for fast performance. And on the other hand, you might have some overnight ETL pipelines, batch jobs, that you just want to optimize for cost. So in that case, they can be completely differently shaped. You might mix in a lot of preemptible VMs to sacrifice a little bit of that predictability of variable job runtime in order to get much better cost savings. In the same vein, not only can you chop up clusters based on the shape of your workloads, but also chop them up in terms of your life cycle. So what this means is on the far end of the spectrum, if you have ephemeral clusters, this really gets rid of a lot of the headaches that come from dealing with high complexity, long-lived clusters. So single-use clusters that are made possible by Google's minute granularity billing and fast deployment time. And this makes it trivially easy to ensure that your hardware is able to evolve in lockstep with the evolution of your workloads. This also means things like even migrating to a whole different region are as trivial as flipping one configuration value in your ongoing ephemeral cluster workload. In the middle ground, there's also this notion of using semi-long-lived clusters. So in this case, instead of using a single very large and forever-lived cluster, chop it up into a small handful of semi-long-lived clusters, where you can still preserve much of the look and feel of an always-on cluster. You'll always have clusters available there, but instead you're sort of load balancing your jobs into individual clusters inside a group, transparently. And by doing so, what you can do is, for example, if you want to canary a brand new version, you get a nice hermetic environment for performing this A/B testing. You can canary one entire cluster unto itself without any risk of leaking over and breaking your other production clusters. But you can canary that with a brand new version. Naturally, let some amount of your production workloads go to that cluster, and if it's all green, it's very easy to now upgrade. Right? You're not trying to change the tires on a moving vehicle anymore. You get to do this in chunks, one cluster at a time. Similarly, you don't have scaling bottlenecks anymore, or single points of failure, because now you can keep adding more clusters to your group in order to increase your scale without worrying about the single bottleneck of scaling. So that brings us to managing your clusters and jobs. So I want to take a look at what it actually feels like to manage your clusters and jobs on Dataproc. And I have slides here for posterity, but we will do this live in demo so you can get a better feel of what it actually looks like. So I mentioned before, a one-liner on the command line, right? And this one is a little bit more complex. The basic command that you'll run is, G-Cloud Dataproc clusters create. Give it a cluster name. And actually, you can hit enter right then if you want. In my case, I'm going to call this dhuo demo 1. I'm going to give it 5 workers. I'm also going to turn on this property for enabling stack driver monitoring, so that we can see how we can build some custom dashboards. Also, I'm going to attach a tag. Just you'll see how that plays into everything. And importantly, I've also put a time command here. So you can keep me honest. We can see how long this cluster actually takes to deploy. So these are all clients that are based on Dataproc's web-based REST interfaces, right? So that means that you get ubiquitous and consistent access from everywhere. excitingly, one of my colleagues is also concurrently using this demo project to do another live demo next door. And while that is doubly tempting for the demo fates, no reason to be worried because we are precisely because we're using different clusters. It doesn't matter if we're sharing the same resources. It's completely safe, right? We can do anything we want. We won't break each other. As I mentioned, so kicked off that cluster from the command line, and sure enough, it's deploying in this web interface, right? So these are different clients all talking to the same REST interface. And it also means that third-party vendors are able to integrate with these same open source REST APIs using auto-generated libraries. So we have native support in things like Apache Airflow, in Luigi, in Python MR Job. So in all these open source projects, you can get Dataproc support out of the box. I'll also show what it looks like to create a cluster entirely from the UI. You just select the dropdown, give it a name, and hit enter. It's that easy, right? So there, I created another cluster. Heck, let's create another one for fun. In this case, I mentioned you might want to use the latest and greatest versions of Hadoop. And what might that entail? Well, we always provide a preview image version which has the latest and greatest software that's going to be targeted for the next release, right? So right now, Hadoop 2.8 hasn't actually been released yet. But we build against snapshots of Hadoop 2.8. So we can select this preview image, and in those 4 clicks, I think that was 4 clicks, we will have a Hadoop 2.8 snapshot. Not official Hadoop 2.8, but a snapshot cluster that lets us be ready for that next release. So going back to here, our time command says that it took 1 minute and 8 seconds. So actually less than 90 seconds. In 68 seconds, we've now deployed a cluster, and it's ready to go. The second that it says that it's done, it is indeed ready. And I'm going to go ahead and run an SSH tunnel. So sounds tricky, but it's really just another one-liner. I'm going to do dynamic port forwarding on port 12345 -n, so it's not taking standard input. And I'm going to start up a new browser pointed at that cluster. And let's see, I have to turn this off. So sure enough, this cluster is ready. This is your standard familiar Yarn UI, right? So we're not locking you out of any of your familiar Hadoop idioms by adding Dataproc. So we have our 5 nodes. This cluster is ready to go. I mentioned being able to submit from raw clients. So let's go ahead and SH into that. Demo-1. So on this cluster, I have access to all my low-level clients. Let's go ahead and run Hadoop jar lib Hadoop MapReduce examples.jar, right? And we can terra-gen some data. And like I mentioned before, also drop-in replacement for HDFS. Instead of specifying an HDFS path, I can I just say gs:// and everything just works magically. Terra-gen. Let's call it temp1. So this is not using Dataproc's Job API. So this is just using the raw Hadoop client. And here's your familiar driver output. It'll tell you the status of your MapReduce job as it goes and everything. And sure enough, as this is running, we'll see it pop up in Yarn, right? So we can see the status of this. And in this case, there's no application tags. This was run raw, not through Dataproc's Jobs API. But at least we can see it works. It just works against GCS without any fancy, without any extra fancy configuration. Alternatively, you can use Dataproc's gcloud command. So jobs submit, specify a cluster, specify a jar file. And I just have the Hadoop MapReduce examples jar local here. I'll just open it a new time, right? So that jar. Standard Hadoop jar file. It's all compatible. I don't have to recompile it to run on Dataproc or anything like that. Pull it out of any Hadoop distro. And I have this local. In this terminal, I'm not SSH'd into the cluster, right? And if I want, I can completely seal off this cluster from the outside world, too. We recently just launched the ability to deploy private IP-only clusters. So you can create clusters that don't have any public IP addresses, and it'll still have, you can still interact with it through all your Dataproc Jobs API, and it still has full access to all GCP services. So let's go ahead and run this. And I'm intentionally running this without any arguments here, just so you can see. there's no SSH session here, but we funnel out the driver output, right? So I made a mistake. I didn't give any arguments, and so the job will fail and print out this help text. It'll tell me, oh, I need to specify an argument, right? So even though I'm not SSH'd in, but Dataproc's client, the job submission client, preserves the look and feel of interacting with these drivers so that you can up arrow and you can have a fast development loop to react to any errors that are coming from your job. So let's go ahead and also specify TerraGen demo TerraGen temp 2. In this case, we are submitting through the Dataproc Jobs API. But just like this, so let's see. I wanted to show these side by side, but my screen's a little smaller. In any case, this look and feel, again, preserves what it feels like to run from your standard Hadoop client, right? So if you have something that likes to stash away the driver output as you're running, it's easy to switch over to the Dataproc Jobs client without changing the way you think about it. And I just did Control-C there. Normally, I'd be out of luck if I did Control-C after running Hadoop jar. But with Dataproc Jobs, you can rejoin waiting for any job, right? So I Control-C'd, but I just have to say wait for that job, and it just rejoins that driver stream right where I left off. I could have thrown away this laptop, opened up a brand new laptop, and continued without skipping a beat. And this also means that that job, so here was that job that, that we intentionally failed. It gave us help text. And here is that job that succeeded, that we just ran. So ubiquitous access from different job clients. You can see the job output here, right? So that makes it very easy. You can check in on your jobs with your phone if you want. It's very convenient. Now, let's see. So going over to stack driver monitoring, we also enabled stack driver monitoring. And one concept I talked about is using this to provide overarching monitoring of multiple different Dataproc clusters in one place. So let's create a group here. We tagged our cluster with, I believe it was dhuo live demo. So let's call it dhuo live demo here. And you can filter by tag. So let's just say that if the tag exists, this constitutes a group. So this way, I can manage multiple Dataproc clusters with the same tag and put them in the same monitoring group. So let's see what it takes to create a brand new monitoring dashboard from scratch and see if we can do it live, right? So I just created a group. Now all I have to do is go in, create a brand new dashboard. It's untitled. I'll call it dhuo demo. And start dragging and dropping to add these charts. You'll see there are built-in host-side monitoring values. And so let's see, network traffic. Let's make it aggregate. So we'll use a stacked area. And we can filter by group. So let's choose our dhuo live demo group. Great, so now we have a chart. Data's going to start coming in. Let's add another chart. We'll add a couple of these. Let's see, outbound is good. Filter. So it's that easy, right? All I had to do, point and click, and I have myself a nice monitoring dashboard. Aside from using stack driver in itself, you can also just click through to your cluster. That was the wrong cluster. Click through to your cluster, and there's already some amount of built-in stuff. So this was our TerraGen job running. So you can see CPU utilization, network bytes, and it pops up. So that we have something more interesting to monitor, let's kick off something a little bit more beefy. So bit of a throwback here. For old time's sake, let's sort a bunch of data. So I think I have some data here. And let's put the output in sort. So I'm going to submit this job, and we're going to sort a bunch of data and see what monitoring looks like. We can also take a peek at logs. So we're well integrated with stack driver logging. And what you can do here is, going through Cloud Dataproc cluster, you can search for dhuo demo-1. And sure enough, we have one cluster there. And as that job kicks off, we have these different categories of logs. We have daemon logs, so you can see about the health of your overall cluster. There's also user logs. So user logs will be associated with each of the jobs. And this is all funneled into Stackdriver so that you can search here. You can actually create log-based metrics, too. So that's something that we recently released as well with a bit of a refactor of our logging. So you can set up monitoring charts and alerts based on what kind of logs are coming through. So here we have the job that we just started, that we just kicked off. So you can see how it's kicking off a lot of individual map tasks, all your usual stuff. Usually you don't have to dig through these unless something goes wrong, right? Now, taking a look, this is kind of taking a long time, right? Like I'm impatient. It took like a minute to get a third of the way through. So what does that mean? Is that like 30 minutes to complete this job? And yeah, we don't have that kind of time. So we're impatient. We want to make it run fast. What can we do? What if we make this thing have 20 times as much resources, right? How hard is it to scale that up? Well, that was about 4 clicks. I lost count, but about 4 clicks later, we resized our cluster up to 100 nodes instead of just 5 nodes, right? It's not quite done yet, right? It's not 100% instantaneous, but the second we clicked that, we saw these GCE VMs start to pop up. So you see these nice green checkboxes. They're starting to come in. They still have a little bit of initialization to do, but as they come in, we're going to see that we have this running job, and in Yarn, we're going to see this active node count start going up, right? So even in the middle of a job, we felt that it was slow, so we can immediately do a couple clicks in the console and immediately start seeing new nodes come in. Well, we'll take another look there. We're also going to, let's go ahead and add a few other monitoring charts. So I used some host-side monitoring. What we did at cluster deployment time was we installed the Stackdriver agent, which reports guest-reported utilization metrics. So this means we can even look at fork rate. Sure, why not? We can look at CPU according to the guest, so that you can see if there's any kind of discrepancy. And this one, I guess, we'll split it out by line, so that instead of stacked, so that way we can see sort of the variability across different nodes. And another thing is that since we've created this dashboard based on this tag that's going to apply to all the VMs, as we add more VMs, it'll automatically become part of this chart, right? As we add more clusters, it'll also become part of this chart if we're tagging those other clusters with the same group tag. So let's see, what else is fun? Memory used. Memory used is likely something that you want to set maybe an alert on or something like this to see. Or when debugging a job, this is where you can potentially look at some skew. So just by hovering over, you can see what kind of skew you're dealing with. So some workers might be using a lot of memory and OOMing, and you'll find that you need to chop up your data differently. So this is also a development tool for your pipelines. I should have come back here earlier. We missed them coming in. But sure enough, we have 100 active nodes, right? So it was that quick. And it comes in faster than it takes to deploy a cluster. We resized it up. In less than a minute, we should have our extra capacity. And also, sure enough, this whole thing sped up. I should have seen it in action, but the second we added all those nodes, this thing sped up. And suddenly, instead of waiting 30 minutes, it's done within the span of basically our demo. So let's see. Once you're done, right. I also created a Hadoop 2 cluster. So just for fun, let's take a peek at that. I think I called that 3, Hadoop 3, or demo 3. So here is the shiny new Hadoop 2.8 UI. Subtly different from Hadoop 2.7, but if you click on About, you can see this is indeed built from a Hadoop 2.8 snapshot. So this cluster will be running Hadoop 2.8 with Spark 2.1. And in general, this is a great way with Canary. If you're doing development, a fast development cycle, then clusters are so throwaway anyways. If something goes wrong, throw it away, and you only lost a couple minutes, right? So generally, you can use this preview image to stay abreast of all the developments in the open source ecosystem and have very agile development against the latest and greatest. So we can wait for that to finish. Once you're done with your clusters, it's just as easy to delete your clusters as it was to create them. You can click some checkboxes, click delete multiple clusters at once if you want. And we're just sorting data. We don't have to watch it finish. So yeah, it's that easy. So that about summarizes it. Let's go back to the slides, and we can recap what we saw. So again, to recap what we saw, Dataproc is built on these web-based REST APIs that allow consistent and ubiquitous access from a variety of clients, both from Google-provided tools like the G-Cloud command line and Cloud Console, as well as third parties for integrations. So there's a thriving ecosystem here of things like Airflow adding orchestration first class for Dataproc, and Luigi and Python MR Job that all integrate with these web-based APIs. We also saw how job submission preserves the look and feel, whether you're using low-level clients or G-Cloud Dataproc Job Submit. But by submitting through the Jobs API, you get this value add of logging, of job tracking, of status tracking, of viewing your job driver output from the Cloud Console, and more to come as well. We also saw that it's trivially easy to update your cluster, even in the middle of a job. So if you underestimated how much resources your job would take and you want to get it done fast, no big deal. No harm done. Click a couple buttons, and you're good to go again. You can speed up that job. And finally, we saw integration with Stackdriver, both on the logging side, where you can see your user logs, you can see your daemon logs, and on the monitoring side, where it's easy to just point and click in order to create customized monitoring dashboards in the same place across different GCP services, so that you can monitor everything, track everything, set up alerts, all through Stackdriver. So let's recap what it looks like to put together everything we learned together. Just to illustrate what this might look like at various stages of your migration. So to begin with, you might have some amount of archival data. You might be looking to free up space on-premise. So you're trying to archive some data to GCS. Maybe you're trying to set up disaster recovery, so backing up your data to GCS already. In such a case, it becomes very natural, even if you're not forcing any kind of compute migration, to start adopting Dataproc ad hoc. So oftentimes, what happens is some kind of unexpected backfill that you otherwise wouldn't be able to accommodate on-premise. No big deal. You can run it, and you can run it quickly on Dataproc, bursting into cloud. New development. Why constrain yourself to working on your development cycle according to whatever scraps are available on-premise, when instead you can sort of burst into cloud and feel free to break things as much as you want, right? And not worry about production as you're doing it. In the interim, you might find yourself with somewhat of a hybrid cloud setup. So by using a VPN tunnel to bridge your on-premise network with a GCE network, Dataproc natively supports deploying onto these same subnetworks so that it can talk natively to your on-premise clusters. And they might be pulling some of the data. They might be helping mediate some of your data transfer. They might also be doing ETL or analytics directly against your on-premise cluster. So either way, they're augmenting your on-premise cluster. And in the meantime, on the other side, you'll find that you still have some subset of things as more of your data starts making use of GCP's storage options. You'll find that you can burst your development pipeline still. So same idea as purely bursting into cloud, but these will be augmenting your overall platform, even with Dataproc clusters that aren't directly accessing your on-premise cluster. And finally, we see a cloud-native architecture where everything is based on cloud storage. And again, instead of any Hadoop cluster being your universe of data analytics tooling, GCP as a whole is your data platform. And you'll be able to unify all of your logging and monitoring across different tools in one place using Stackdriver. You might find third-party tools to be useful for performing your scheduling and orchestration and productionization of your Dataproc jobs. And you'll likely find some mixture of completely ephemeral jobs that are very hands-off, easy to manage, while others that might not have come along so easily, but still are amenable to semi-long-lived clusters. And again, with semi-long-lived clusters, you still eliminate the headaches of worrying about this 2-year-old cluster where you're worried that a gust of wind might blow it over and you don't want to touch it. Right here, you can canary brand new versions of software, and if if a new guy comes in and breaks an entire production cluster, no big deal, right? You throw it away, create a new one, let it join the group, and it's that easy to manage your infrastructure. So that pretty much concludes today's session. A couple of related sessions include this afternoon, there's going to be BD 205, which is a more higher level view of Dataproc with some neat demos, less migration oriented. Machine learning on Spark MLlib is going to be tomorrow morning. And IO 321 was concurrent with this one, but you can catch it on recorded sessions if you have the time for a deeper infrastructure level dive into GCS performance. Just some doc links. You can find a lot of good reading materials under cloud.google.com/Dataproc. You can also see those initialization actions I talked about hosted on GitHub and maintained by the Google team along with a lot of ecosystem contributions. And various sources of help. Naturally, you have your cloud support contracts where you can contact high-level escalations of cloud support troubleshooting. There's also a very active Stack Overflow community. And of course, under our normal cloud.google.com documentation, you can find a lot of helpful links. So thanks.